buenos días para todas las personas que nos acompañan en esta mañana. Segundo Encuentro Internacional de Robótica Corhuila 2022. Es un gusto para mí acompañarlos en esta conferencia, un espacio con un ponente internacional. Desde Japón nos acompaña Eishi Yoshida, quien se encuentra conectado. Queremos darle la bienvenida. Por favor, Sebastián, que está en el máster, si nos ayuda para hacer la conexión y poderlo saludar. Okay, good morning, Mr. Eishi Yoshida. Nice to meet you. Thank you for being here.
Buenos días.
Muy buenos días. So, Mr. Eishi Yoshida is from Japan. He is a robotic professor and researcher of Tokyo University of Technology. It's a very pleasure to have you here as a speaker. So very welcome to Colombia, especially to Neiva. Thanks for being here. And thank you for your participation in the second International Robotic Meeting Corhuila 2022. Please, we invite you to start your presentation. Humanoid as a platform observer, physical human Howard's motion understanding system. So please take the word, and thank you for being here again.
Thank you very much for your kind introduction. Can you hear me?
Yes, perfectly.
Okay, so thank you very much for inviting me to this event. Actually, I'm from Tokyo University of Science, but formally, I belong to AIST, research institute called AIST, and I had spent some time with Mario. So Mario, thank you very much for your invitation. So today, I'd like to talk about Humanoid as a platform of cyber-physical human towards motion understanding and synthesis. So I have been working on humanoid robotics. So of course, there are many recently, especially there are many good humanoid platforms, as you can see here, like Boston Dynamics robots, and also in AIST, we have been working on this HRP series robot, and also there are many other great platforms. So humanoids has been attracting, especially robotics researchers. So also, I have been involved to edition of some books, humanoid motion planning, and handbook of robotics, and also recently this book of humanoid robotics a reference. There is a huge work, and I also contributed to the part motion planning here. So of course, humanoid robots are expected to be used in industry or other heavy, especially heavy large-scale assembly. You know, here, like in the assembly of airplane. Also, recently, in also the working with humans in production. Of course, labor shortage is a severe problem in everywhere in the world. But also, humanoids attract people, researchers, because it can be used tools for robotics research into humans. To understand human, we can also use humanoid robots, and these robots, for example, can evaluate the device that human use. So by combining with digital human, this is a digital model of human, we can have more possibility of humanoid robots to understand human motion and also synthesize human motions. Here, this is what I call cyber physical human CPH. Here, of course, human is a target. So this is a target for motion planning, motion generation by human robots, but we can't really see what happens inside. So it's very difficult to measure inside. But by using, if we can have a human robot that is very close to human, we can measure internal states. But it's very difficult to have many human robots, so we can take advantage of simulations, digital humans like this, by changing the parameters of size and also other body parameters. So we can use in a complementary manner to do the research on humans by combining them as a cyber physical human, and we can also augment the data. So today's talk, I will be talking about several topics, and in this robotics research, this is rather classified in the model-based approach. That means we have model of the robot, and to control it or optimize its motions. For example, human motion, what we call human motion retargeting, where humanoid reproduces human motions to evaluate wearable devices. And this research has been also applied to set up some standard for wearable robots. And we combine this with digital human, like this, human model, and also to design some devices that human uses, like by using also digital human model and some optimization. Also, I will talk about that. So let's start with this physical reproduction. So as I told earlier, so we measure human motions because we suppose that human optimizes something and try to reproduce by it, of course, by using motion capture and retargeting. And also we try to extract or identify some important factors or some invariants, latent space that governs human motions. And then we can do it feedback to test in the real motion. So the first topic is the evaluation of wearable devices by human robots. So this device, it's a support suit that has elastic band on the backside, and when you bend down, it stretches and it supports your upper body weight, so that to prevent lower back ache. And then we measured human motion by motion capture system and reproduce it by human robots. So it can wear this suit without any changes of its design. So if the robot can reproduce the human motion very well, it can be used to evaluate it, because now if we do human subject, the experience with human subjects, it's very difficult to do any quantitative evaluation. So we can see that by wearing it, so the robot shows that the forces, the torques applied at the lower back is reduced. So we can quantitatively demonstrate its effect. So the important technology for this is human motion retargeting. So we measure human motion, and then by applying some optimization technique, we reproduce by human robot. And this work with Dr. Ayusawa in AIST, it can byproduct human motion with robot constraint, which means that what could be the motion you make when you have the same constraint as a robot. So this shows that we can know that what kind of motions, what classes of motions the robot can very well reproduce the human motion. So we tested for different types of motions, lifting up and also the doing some transfer, object transfer. I hope the video is working. I don't know, it is far from Colombia in Japan, so I don't know. I hope the video is working. But like this, so this general method can allows reproducing human motions by human robot. Of course, there's some speed limit, but you can see that the robot makes natural motions. So this is the motion without walking, but the optimization technique we can also integrate what we call walking pattern generator. So we measure this kind of motion. This is a kind of installation motion, and then we can also apply the same technology to reproduce the walking motion by human robots. So I showed that the test with the support suit, and this is another more powerful device called muscle suit. It has very powerful pneumatic actuator inside inside, and allows you to lift very heavy objects. It's very powerful. So if we just reproduce human motion, if it's not with moving with a good timing with the device, we cannot really evaluate the device. Even we may break the robot because this device is very powerful. So we extended this reproduction motion by using the external force sensor, and when the robot feels that it is the support starting, the motion starts, and then we measure also the torque, that here of the robot motor, and then we see that, and then compare the force with the joint torque without this device, and then we can see that if this curve is below, it shows that the robot has very heavy load, but we can see that it's greatly improved. So more than several tens of Newton meter is supported by this device. So we showed this kind of quantitative effect for the first time. So we also tested with the humans, which means that robot in this control, robots make the maximum of the external support by the device, and also we tested with the human. We measured mass activities, and we can see that when the robot, when the device starts producing power, human also has very low power during the motion. So it shows that our control is also corresponds to the human motion behavior. In Japan, especially, there have been many devices, supported device to this kind, to help you lift up heavy objects. So we applied this technology to when we developed this very simplified dummy, active dummy, that can also wear this kind of wearable devices. Then also we show that the human lifting up motion can be very well modeled by the same kind of equations. And then here you have the where device and this without. So we do the same motion with and without and measure the force and torque applied this part. So this kind of standard is important when you do some choice of the product. When you choose the product, like car, you may choose the powerful car or very efficient car. So this criteria shows that this is the what kind of force it can produce, and also how much it can reduce the load applied the lower back. And then there's different timing. So it's a long time timing or a very peak powerful timing. So this kind of standard allows you to choose the appropriate product according to your usage. So just briefly, this research has been adopted to Japan industrial standard, and recently it has also been adopted for the ISO. Next, so the digital human model. So till now it was humanoid, and then now digital human model. So digital human model, you can change its shape, property. We had a database of human shape, and we added elderly people, the shape of the elderly people. So as you can see here, when you get older, unfortunately, you lose the force to keep your shape. So it's against the gravity. And then by using the principal component analysis, we have the parameter of age to change the age. And you can also change the parameters like height and weight. So it can be used to simulate different types of human. And then, for example, we can do the compute in the simulation when this kind of digital human uses the devices, what kind of force is applied. So of course we need to do some approximation, but try to very precise by using this shape model according to the different parameters, and then we compute the forces. For example, this is a supportive device to transfer people, and this is the measured force. And then this is simulation, so we can see that it is very close, and we can test the pressures applied to the different shape of people. This allows you to reduce the hardware prototyping. If you do the several design loop in the computer, it greatly reduces the effort to do the real hardware prototypes. This is another example. We had a joint research with a company who produces and sells the restroom equipment. So when you when you stand up in the restroom, so heavy load is applied at the knee. So usually we put this kind of bar to help you to reduce the force applied at the knee. But ethically, the appearance, the people don't often like this. So by putting a small shelf here, it can produce the same effect, which means that this analysis shows that more choice of the design of your living space. This is another usage of the digital human, and another extension of is human motion analysis. We can measure the human motion, and we also apply the what we call musculoskeletal model. So it has a skeleton with hundreds of muscles. When you move the motion and the force, we can estimate what kind of force is produced by these muscles. Of course, there are so many, so you can't compute each of them, but we do some optimization to meet the dynamic physical dynamics and also to minimize effort. By doing this kind of optimization, we can estimate which part of the muscle is most producing the force. So we need to think about the muscles can't push; it can only pull. This kind of constraint should be also be considered. And then by extending this computation, we can estimate what we call joint reaction force, which is how much force is applied on the lower back between the bones. And then we can do this computation in real time. So this person is lifting a heavy object. And then you can see here the real-time estimation of the muscle activities and also the lower back pressure here. So you can see that when you lift the heavy object, we can estimate the force pressure applied at lower back, and then when it exceeds some threshold, it can also show it can give some warning by changing the color of the display. So this is with the motion capture system, which means that you have a unique camera, but by using what we call IMU, inertial sensors. So this is free of camera. You have inertial sensors that these inertial sensors, the smallest one you have also in your smartphone, and this doesn't have this camera space constraint. And then we applied the same technology, so you can measure and estimate the muscle activities. So, for example, it can be used to monitor the load of workers in the factory. So when you, for example, if you get tired, if the system finds that you're very tired, for example, it can advise you to take a rest. So one application is to design the assistive device. This is a device to transfer the user from one position to another, from the chair to the restroom, to the chair from the bed to the wheelchair. So it has 2 degrees of freedom, so height and rotation. Even though it is very simple mechanism, its motion, it can be, you have infinity of possibilities. So how to design this one? So we can use this digital human technology. So we include the device in the digital human model, and analyze the force. When you use this, we want to reduce the force applied to this part on the arm, or we may want to reduce the forces applied to the knee depending on the status of the user, the patient. So by giving different types of cost function, the motion may be different. So first turn and lift, or first lift and turn. This may the difference. This may give the difference of to reduce to the force flow, to to reduce the force applied to the knee or the force applied to the under the arm. So till now, I have been talking about the motion optimization. So it is formulated to optimize the motion. This is the what we call trajectory, some physical quantity, and under some constraints. The constraints is the maximum force or joint motion limit. So we have developed some methods to efficiently compute this trajectory. And this is one example for humanoid robots. So this is robot motion involving multiple contacts. So we generated this kind of motion. So, and then we may add different constraints to differentiate the motions. For example, here, if the robot has a locked knee, or if the robot has the sore foot, we can give some constraints that you need to fix the knee angle to a certain angle or reduce the force applied this part. So without the constraints, this is the walking motion. This is just the result of optimization. If you give the locked knee constraints, the robot walks, but you can see that it tries to keep the angle here. So you just make the outward rotation of the the foot, and also here, if you have a sore knee, so it uses its upper body to reduce the force applied at this part. So when you touch this the sore foot, the robot uses upper body to reduce the force applied at this foot. So this shows that you may simulate different impairment motions by giving different constraints. So far, I have been showing some research on the human motion reproduction by human robots, or product design by physical human. So by combining humanoid and digital human as a cyber physical human. So the challenge is that beyond the model-based approach, so till now, this has been the model-based approach. Model-based, that you have a model of the robot and do some optimization. But when you do some more complex motion with a lot of contacts, it is very difficult to have precise model. And also, what could be the underlying human optimization strategy? So nowadays, the machine learning techniques has made a lot of progress. So we may combine this machine learning technique by the model-based approach. So I started a new project after moving to the university from the JSP, the organization called organization called JSPS. So data-driven learning, prediction, and generation of whole body contact motions based on cyber physical model. So this is the the model I showed at the beginning, the cyber physical human. I put I for interactive. So we try to define the general dynamics description for anthropomorphic system that can be used for human or humanoids, and learning the contact motion as a network. So by using also by combining model-based method and building more up high level description like a symbol. So model-based approach can be used to describe the very complex robot systems with a huge number of parameters. And then the machine learning doesn't have to take care of all the complex dynamics because we already try to simplify the description of complex system by model-based system. So I hope that this kind of machine learning can be more effectively applied to this to learn different contact motions, and then apply further learning to symbolize the contact motion. So we can try to describe the different types of contact motions. So this is the end of my talk. Thank you for your attention.
One second. Can you hear me right now?
Yes.
Okay, Mr. Eiichi Yoshida, thank you so much for being here as a speaker.
Thank you very much.
I want to read two questions that we have, but before I want to mention and to thankful the people who make possible the second Robotic International meeting, Corhuila to 2022. So I want to read it. I want to mention is Gobernación del Huila, Expo Huila Fest, Cámara de Comercio del Huila, Confamiliar, Sony App, Robotics Kids, TED Drop Robótica, Pixie Minds, Ato Electronic Equipos, Alicis y Gestores del Conocimiento. There are persons and companies who make possible to have you here. Also to Corhuila, and especially to our program, Ingeniería Mecatrónica. And now I'm going to read two questions, Mr. Eiichi Yoshida.
Yes.
Okay, Sebastian said, ask, Mr. Yoshida, excellent work. Thanks for sharing your knowledge. I want to ask you something. Will the Earth one day be dominated by robotic as seen in the movies? You can read it also.
Yeah, so I think this is a question related to the artificial intelligence, right? So I don't know. I'm very skeptical that artificial intelligence can kind of invade human society. So I think for the moment, the artificial intelligence can do what we ask you to learn. So I hope the robot will be partner of our society to help us and to live with us. Thank you for your question. I hope I answer the question.
Thank you, Mr. Eiichi Yoshida. I'm going to read another question. It's from Mario Ricardo Arbulu.
Mm-hmm.
It says, Mr. Yoshida, what are the public policies to introduce avatars on duty environments? I guess that is policies instead policies.
So I think it is. I don't know if the public policies has been defined, but these days you have a COVID, So remote work is very popular now. So we can now what we can do is that doing the telework or video conference. But I think in the near future we can use this teleworking in the physical work. So you can do the you are teleoperating the remote robot to do the task, physical task. So which allows you so that you can, for example, you work in your home to do some research in the factory. So this is kind of a dream, but I hope now in the future society, it will become possible. I hope it will become possible. You can work whenever you are and wherever you are. I hope I answered the question. I don't know.
I guess you are. And just before finishing this conversation, one question more is from Julian David Ramirez. What was your inspiration to enter the world of robotics?
You know that when I was a child, there's a lot of cartoons. I don't know if you know the cartoon called Doraemon.
With the cars?
The cartoon, no, Doraemon is a robot.
I'm not
cat type robot that can help you, and he had this robot has a small pocket that you can bring. From he can bring out any kind of futuristic tools to help the main caster of the child. So cartoons and maybe movies gave me a lot of inspirations.
Okay, so in the beginning, cartoons and movies were your inspiration, right?
Yeah.
Okay, Mr. Eishi Yoshida, thank you so much for your time, for being here in between and through the technology. But it's amazing for us to have you here. Thank you so much. Have a great day.
I hope you liked the talk. I don't see the reaction, but thank you very much for inviting.
Okay, so I'm sorry. After we finish the meeting, I'm gonna send you where you can see the people speak and talk about the meeting. Thank you so much.
Thank you, Mario. See you, Mario.
Del 8 al 10 de septiembre participa en el Segundo Encuentro Internacional de Robótica Corhuila 2022, un evento que reunirá expertos nacionales e internacionales en temas de robótica.
Los invito al Segundo Encuentro Internacional de Robótica que desarrollará Corhuila, en Neiva, Huila,
donde habrán ponentes internacionales de alto impacto en temáticas de robótica. Habrá interacción social con robots que traeremos al evento para que ustedes puedan charlar con ellos.
Hi, I'm Kensuke Harada from Osaka University. I would like to kindly invite you to participate the Second International Corhuila.
Hola a todos, mi nombre es Giovanna Estefanía Ramírez Ruiz, ingeniera electrónica y futura astronauta colombiana. Un evento que se desarrollará el día 7 de septiembre de 10 a 11 de la mañana. Este evento ha sido organizado por Corhuila en el marco del Segundo Encuentro Internacional de Robótica Corhuila 2022. No faltes.
Tendremos conferencistas, showrooms con robots de tamaño real y competencias en todas las categorías: primera infancia, infantil, prejuvenil, juvenil y universitarios. Participa y disfruta de este espacio educativo para niños, jóvenes y adultos. Te esperamos del 8 al 10 de septiembre en el Club Los Lagos. Adquiere tu boleta comunicándote ya al 322-873-5281.